Thank you very much, Michelle, and thank you all for being here. It's a pleasure to be part of this course on Indian knowledge systems and to look at some of the material that I often deal with in the broader context of intellectual history as a whole. What have Indian knowledge systems, how have they combined to help produce this development? How have they interacted with each other? And how can we use these interactions to try to figure out, as historians, what's actually gone on in the past? And I'm hoping that this will serve as a sort of zoom in on a small part of Professor Srinivas's brilliant talk in yesterday's class, where he was looking at a very broad cross-section of Indian scientific traditions. So as I'd say, I'm examining one rather specific development, both within the Indian culture areas where it emerged and outside it in the cultures that received it, and trying to figure out and trying to explain how we can use the various evidence that we get from the historical sources to attempt to construct a narrative of what actually happened. So, for just a general overview of what I hope to do is, it sounds as though the basic introduction to decimal place value numbers has been taken care of, so we will just touch that lightly. And then we will start discussing this question of the Indian origins of such a system, which I'm abbreviating as DPV here to save space. And then we'll get into the historiographically interesting stuff, the challenges that we encounter in trying to reconstruct the origins of this system, and find out, examine what we know about how the system spread within Indian culture areas, and how it was received as an exotic or form of foreign knowledge some time after that. And finally, looking into issues of more recent historiography, just tracking a bit of the process of the historical erasure and then the recovery of this narrative of the Indian origins of the decimal place value system, as historians outside India have become more aware of things that have been going on. And do feel free to, if you have a brief question or a clarification that is needed during the course of the talk, just grab my attention and we'll deal with it. All right, yes, the decimal place value system. We're looking at it specifically here because it is so so much second nature to almost anybody in the modern world that we sometimes forget the specific the mathematical or cognitive features that make it what it is. Of course, all that it's about is having these 10 distinct glyphs or digits that are valued in a number depending on their position. That is, what is the power of the base that is multiplied by this given digit to give you a part of the number. This example of 138, which is just 8 times 1, or 10 to the 0, plus 3 times 10 to the first, or 10, plus 1 times 10 squared, or 100. Okay. And this is the system that we're tracking from its emergence about 2,000 years ago here in India. Now, just to kind of give ourselves a framework to look at this development, let's also note that there are many other types of number systems that use this same positional principle, although with a different numerical base. And of course, there are many number systems that also use a decimal base, but not the positional principle. The most familiar of a example of a positional system with a different base is, of course, the so-called sexagesimal system, or base 60, which you see, do you see? Yes, over the door there. You have strictly speaking, 60 distinct digits, so to speak, ranging from 0 to 59, and you multiply those by powers of 60 and add them up in order to figure out what the total is. So here's an example where you have 1230 hours, which is, of course, really just 12 times 60 plus 30, or half of 60, and you get a decimal equivalent in minutes. This is, in fact, considerably older, almost twice as old as the decimal place value system. It emerged from in cuneiform writing during the Neo-Sumerian period, around 2000 years before the Common Era, in Mesopotamia, so what became ancient Babylonian civilization. Then we get into more recent developments of number systems. People are probably familiar with the, at least the notion of the base 2 or binary system, in which you only have 2 digits, 0 and 1, but of course can represent any integer with these, just multiplying them by successive powers of 2 and adding up those. You will see a number, in popular representations, a number of references in various situations to so-and-so or such and such a development having invented binary numbers ranging to thousands of years in the past. And, that just reflects the fact that a binary system is, to some extent, implicit in a variety of different calculation and representation systems. We start getting explicit numerical presentations of such a system in early modern Europe around 450, 500 years ago. Then, of course, there's the younger cousin of the whole system, hexadecimal, octal, any usually using powers of 2 as the base for computing, making digital computing with modern electronic computers easier. But the basic principle of place value in all of them is the same. And I think I will skip this example of using the letter B to represent a digit greater than 10 and so forth. All right, so once we have that, we know what it is that we're talking about that has originated in the context we're looking at. What we'd first like to establish is what are the contributing factors that played a role in that? What are the forms of knowledge, the intellectual and cultural heritage that gave us the building blocks for the decimal place value system we have now? And the most fundamental of those is the decimal number words, that is extremely ancient system, in fact, is shared with other Indo-European languages, from the Celtic and Germanic to the Indo-Iranian, and probably goes back as far as Proto-Indo-European, the common ancestor, where the verbal form of verbal ways of representing numbers with number words just happens to be exclusively decimal, or the organized, structured system for doing so is intrinsically decimal, in that when we speak in any of our Indo-European languages, from Indic to Celtic or anywhere in between, we have a concept of what we call single-digit numbers, the units, the tens, the hundreds, the thousands, the 10,000s, and so forth. Here's an example from the Rig Veda, going back thousands of years, a reference to Trini Shata, Tri Sahasrani, Trimshachcha, Navacha, literally 300, 3,000, and 30 and 9, or as we would say, 3,339. This is, of course, just to drive this point home, separate from a place value number system. You don't need place value. You can't use place value, in fact, in a system of verbal number words because you have these labels, tens, teens, 30s, hundreds, thousands that are attached to the word to tell you which power of 10 it refers to. This 3339 here is just that I've written is just a modern transcription of that. We also have, as Professor Srinivas mentioned yesterday, references as early as late centuries before the Common Era to a written symbol that in some sense was used to stand for nothing or emptiness. So this is the shunya, not necessarily an arithmetic zero as used in mathematical calculations, but definitely in many contexts a symbolic zero, or a way of writing, in a simple form, there is nothing here. What we have in the at the level of written characters in the same approximate time period, late BCE, is a variety of epigraphic evidence, that is from stone inscriptions and copper plate inscriptions and so forth, of numerals that are decimal but not place value. And you can see from some of the examples in this useful table by S. Gokhale that they range from documented evidence from just a few tally-like slashes to represent small integers to more complicated systems, as we see in the Nanagat inscriptions, with separate glyphs for 4, 6, 7, 9, and so forth. But you see, the violation or the disconnect with place value comes here when we get into 10 and 20, which are not just the symbols for 1 and 2 written in a different place, but which are in fact entirely different symbols. Same goes for the 100 and 200. So these are the building blocks of written numbers as they occur in Indic script. And I'm sure a number of them will seem, they'll look sort of vaguely familiar to you from the decimal digits that we now have. And, because of their ancestral role, that's not surprising. So, these are the materials that we know exist before there is any evidence for the decimal place value system as a whole. And, where do we go from there? Then we have to leapfrog about half a millennium to get to a point where we have definite, incontrovertible evidence for the existence of the decimal place value system itself. And as so often happens with developments in history of science, very few inventions or innovations or origins are really preserved in their initial form. People don't write down when they are in the process of inventing something. If they do write it down, it doesn't tend to get saved. We see one mature system, and then that continues, and then gradually we see that being replaced in the documentary evidence by another mature system. And what we have to do is try to figure out how the process of maturation happened in between. So what we have, where this new maturity appears for us in decimal place value, is, as Professor Srinivas also mentioned yesterday, the astronomical and mathematical work called Aryabhatiya of Aryabhata, written sometime right around 500, year 500 of the Common Era. And although it doesn't discuss decimal place value in an explicit way, or as it doesn't discuss it as a concept, it's very clear that Aryabhata is assuming familiarity with it on the part of his readers, because he invokes arithmetic and representational methods that require you to be manipulating decimal place value digits to get a correct answer. So here's a nice little example of Aryabhata's verse on square root extraction, again mentioned briefly by Professor Srinivas. And what he says, leaving you to look at the Sanskrit transcription there, is more or less that one should divide constantly the non-square places by twice the square root. When the square has been subtracted from the square place, the quotient is the root in a different place. How many people have had to learn to extract square roots by hand? And then you point, yeah, a few people, and I'm sure, Michelle, you must have had that. Yes, often I'm giving lectures at home. You can see the generational divide very clearly among those who have had to learn in school how to take roots by hand and those who have not. But this, of course, is a very a terse elliptical way of expressing the algorithm. You couldn't, it would be difficult to figure out on your own exactly what it meant just from this one verse. But the relevant point here is that it requires you to lay out the number whose square root you want to take as a sequence of consecutive digits which alternate between being square, varga, as he says, or non-square, avarga in Sanskrit. That is, respectively, the even or the odd powers of the base 10. So the perfect square places in a decimal number include the 10 to the zeros place, the units, 10 squared, or the hundreds, since 100 is a perfect square, 10 to the fourth or 10,000, and so on. The odd places are non-square, 10 to the first, 10 to the third, 10 to the fifth. These are all not perfect squares. And how that works, just to give a brief example that we won't look at in, we won't run through the calculation in any great detail, but if I consider this number 341,056 and I wish to take its square root, you probably have a vague recollection, if you have studied this, of having to lay out the number, grouping the digits in pairs, and then find a square and subtract it from the first two digits, and so on and so forth. And that is basically what Aryabhata's technique requires you to do here. I have denoted the square places, the even powers of 10 with little squares, and the non-square places with little triangles. And you can kind of see how these successive steps in the algorithm correspond to these very brief references Aryabhata's verse makes to subtracting a square from the square place, subtracting the root times the quotient times twice the root from the non-square place. And you are essentially just pulling out all the accumulated factors of this square number from the number itself, and you end up with a collection of successively acquired digits, the 5 and the 8 and the 4 that are marked in red here, to give you the ultimately the root of this perfect square, 584. And I hope it is apparent from the layout here that to manipulate an algorithm like this requires the number to be set up in decimal place value in order to work. You could, of course, have comparable equivalent algorithms working on numbers in different positional bases, but it's the positional principle with these and the manipulation of these digits that makes that possible. All right, so that is as deep as we will get into any actual mathematical calculation here. Just want to show you that we're not trying to mislead anybody when we say that we're sure that the decimal place value system is firmly in place by Aryabhata's time around 500. And moving beyond that, we begin to collect evidence that's actually physically recorded and preserved in inscriptions, many of the earliest ones occurring in Southeast Asia rather than in South Asia itself, as Professor Srinivas noted, in which these forms of the 10 decimal digit glyphs from 1 to 9 and then 0 are probably going to look quite familiar from the decimal digits in various Indic scripts that you've already seen. So either the mathematical principle, we can tell from the text is obviously there. The forms of the numerals, we can tell from the inscriptions are there at least somewhat later. Obviously, the system is established. All right. And we have, as Professor Srinivas also referred to, the additional evidence in the form of schemes for verbally encoding decimal place value numbers that are attested in Sanskrit verse texts from at least the 6th century of the Common Era, and probably considerably before that. So why would you need such a thing? Well, if you have attempted to compose anything in metrical verse or rhyming verse or anything that has to follow a certain verbal pattern, and if you've tried to put numbers in it, you will have noticed that they're a bit intractable, because a given number usually has only one way to express it in words, and number words tend not to rhyme with anything very much, and they also tend to have rather rigid metrical form. So if you are composing your technical literature, as you are in the Sanskrit-speaking world, in metrical verse, you need to have a more flexible way of referring to numbers. And there are two major ways of doing that in classical Sanskrit scientific literature, as Professor Srinivas briefly mentioned. One of these is the so-called bhütasamkhya system that simply replaces the names of digits or small groups of digits with the names of objects or concepts that are naturally associated with those digits. So any word meaning hand in Sanskrit can also be used to represent the number 2. Any word that's there being 2 hands on our bilateral symmetry here. A word for moon can be used to represent the number 1. And there are dozens of such examples. If you have a bhütasamkhya encoding that consists of the Sanskrit word danta chandra, tooth and moon, well, you start from the lowest significant digits. So tooth naturally stands for what number? How many teeth are there? In the human mouth, of course, there's lots of species, but 32. Yes, if you have all your wisdom teeth, then there will be 32. Moon, of course, as I said, stands for 1. So you can see how this likewise is intrinsically and necessarily place value, because you can't just randomly combine encodings for the number 32 and the number 1 and come up with this positional number 132 unless you have a place value system clearly understood and the order of the presentation of digits. So in addition to the bhütasamkhya system, there's an even more flexibly encoded version, the so-called Katapayadi system, which we see originating and almost exclusively used in South Indian texts. And this is a quite elegant technique, one-to-one, or not one-to-many mapping, that assigns the numerical values of the digits from 0 to 9 to different Sanskrit consonants. So those who have a little bit of Sanskrit will be able to see why it is called katapayadi, that is beginning with ka, ta, pa, and ya, because those are the consonants that are assigned to the digit 1, and ka, ta, pa, and ra are assigned to the digit 2, and so on. Now, the digits that the consonants that I've marked in red here are the ones that occur in this example I've given, tatwa loke, which is something that appears in an inscription in the late first millennium. So how we would interpret that numerically is by looking at the consonant of the first syllable, ta, which represents, or it is assigned to 6. And then we have a conjunct consonant here, tatawa, but in the Katapayadi system, it is understood that only the last consonant in a conjunct counts. So we look at the value of wa, and that is 3. The consonant of lo is la, va represents 4. The la in lo represents 3. And of course, the ka in k is 1. So this is the sequence of digits from the least significant to the most of 6, 4, 3, 1, or 1,346. Again, a very nice, elegant system, and poetically very convenient because, as you see in this example, you can use actual Sanskrit words to represent your numbers, and you can then have, as in the Chandravakyas that Professor Srinivas mentioned, an entire stream of numerical values which you would find very difficult to memorize in its numerical form, but if it's encoded in a bunch of little Sanskrit mnemonic words and sentences, it's much easier to retain. And again, the key feature of this is that the occurrence of a Katapayadi system or any related encoding system like the bhütasamkhya system is an incontrovertible marker of the use of decimal place value. You cannot understand such an encoding system unless you have a recognized positional structure in the numbers that you're talking about. Yes. Yes. So this is in this syllable. So that's a conjunct consonant. But in the Katapayadi system, it is a convention that only the final consonant in a conjunct counts as the numerical value. So the consonant in that syllable, twa, that contributes to the numerical meaning is the va. And the va stands for, oh, you know what? I see why this is not so obvious to you, because you don't have the rubrication, the red letters that I see it quite clearly on my screen here, what the part that I have marked in red, but you can't see. You have just black and white projection. Okay, sorry. Can you sort of see, you get a little redness there? Sorry. Does that help? Yes. That's right. Yes, you start from the least significant digit, that is from the units place first in setting out your stream of digits, and then you just have to be aware that that is the order. That is that there is a famous mnemonic referencing that, saying that you proceed from the least significant to the most significant. But the Sanskrit phrase has slipped my mind. Is that clear now? That so you end up when you say tatva loke, you have the ta and the va and the la and the ka, and that makes the sequence 6, 4, 3, 1. But you understand that in reverse as 1,346. Other questions? Yeah. Okay. So where we are end up with, they're looking at these historical brackets on this development, the state of numerical representation at a time we know is before this period, and the state of numbers at a time when we know that DPV is firmly established, can be summarized by noting that there seems to be no evidence for use of such a system prior to the Common Era. All our known inscriptions from before the Common Era are non-place value numerals. And by 500 CE, we've got not only evidence for the use of such a system, but for its very sophisticated establishment. So it's what appears in the work of Aryabhatta and his slightly later contemporaries and successors is a very mature and sophisticated system with associated the use of zero, both arithmetically and notationally, and sophisticated representation and calculation methods. All right, so that gives us 500 years as historians to try to narrow down what's going on or what went on in this period. Can we produce a better, a tighter chronology on the sequence of events here, and maybe get closer to figuring out exactly where, when, how, why, by whom this innovation was made. And one of the things that gives us a clue is, again, was briefly alluded to by Professor Srinivas, that is passing references in philosophical works in the sort of metaphorical sense to the principle of place value. That is, in a Buddhist text from the 4th or 5th century that's attributed to Vasamitra in the 1st century or 2nd, there's a remark that it has to do with the concept of the unchanging nature of an object that can be perceived in different contexts or roles. That is, when a clay counting piece is in the units place, it's denoted 1, in the hundreds place 100, in the thousands place 1,000. And this is actually picking up on the topic of the abacus that was mentioned earlier, because this system of a place value counting pits into which you put a number of tokens to represent how many units, how many tens, hundreds, or thousands you have, is in fact a mechanically equivalent to, or computationally equivalent to the abacus devices that we were talking about. Similarly, a later commentary on the Yoga Sutra of Patanjali makes this nice simile of a line denoting 100 or 10 or 1, depending which place it's in. The same woman can be called, referred to as a mother or daughter or sister. And these, unfortunately for our attempt to be more historically precise here, we can't be sure that these are referencing, fully so-called ciphered positional decimal place value systems of the sort we're familiar with and that Aryabhatta was using. They could have been a sort of hybrid of place value and tally mark systems. So in this example here, I can write down a 1 stroke in on the left side and 4 strokes in the middle and 2 strokes on the right. And if I say that those places refer to the hundreds and the tens and the units, then I have essentially written down a place value representation of the number 142. But of course, without the separate glyphs, the separate forms of the digits for each number, I don't have the computational convenience that I have in the more fully developed system. So we cannot assume that this means that, the Yoga Sutra era was familiar with the decimal place value system. Okay, and then we get to attempts to reconstruct the origins, to narrow down these possibilities. And here, I'm afraid, we have a record of failure to describe, but it's important to bring it up because, for one thing, that is something that my book that you're passing around there is wrong about. Prior to it was being published, prior to subsequent re-examination of this material, I was accepting this very reasonable inference in the work of David Pingree, published in 1978, when he edited and translated the ancient Sanskrit astrological text, Yavana Jataka, meaning the horoscopy of the Greeks. And he read in the manuscripts of this work that he had the compound word Narayanankendu. That is the compound of Narayana, Anka, and Indu, and took that as the very familiar seeming bhütasamkhya number, a chronogram or a date encoding, which consists of words for Vishnu, for hook, and for moon, which are in the later text very recognized bhütasamkhya synonyms for the digits 1 Vishnu, hook, and Anka refers to 9 because of its shape, and moon, of course, for 1. And this, in the context, seems to refer to year 191 of the Shaka era, or equivalently about 269, 270 of the Common Era. So this is when this sort of thing works, it's a very nice, elegant way of using our textual evidence to figure out historical developments. That is, this would be evidence that decimal place value numbers with the bhütasamkhya encoding system were already fully developed by the time this date was written, that is, around the mid-3rd century. Great, but of course, somebody's always got to be picking things over. In 2013, Bill Mack, in an article in the History of Science in South Asia, found in a Yavana Jataka manuscript that had not been looked at that the presumed bhütasamkhya number that Pingree thought he read was in fact a mistake for a non-numeric compound, Narayana Arka Indu, which was simply a reference, not uncommon, not what you would expect to find in an astrological text, to Vishnu and Arka the sun and Indu the moon. So here's a nice little image of the manuscript. Gosh, that's still a little dim there, but with more illumination, you can see that that is an Arka and not an Anka. So the Max translation seems more plausible, and consequently, this work, the composition of the Yavana Jataka, although it doesn't disprove the existence of decimal place value numbers in this period, also doesn't corroborate them. So it's inconclusive for this proposed 3rd century dating of the decimal place value number system. All right, yes. Mm-hmm. Yes. Because Arka, good question, but in the bhütasamkhya system, the word Arka for sun does not stand for 1. You would think it might, but does anyone have an idea or a knowledge of or a guess as to what number arka, the word for sun, does refer to. Same for Surya, same for Aditya, same for any synonym for sun. Is there a guess? It is 12. Why is it 12? Or 12 suns, yeah, 12 Adityas and 12 solar months in a year. So you cannot get a reasonable date out of the chronogram 1-12-1. So in this case, at least not unless you were looking at a very, very extended calendar system. So unfortunately, we have to, as always, it's the manuscripts that ultimately have to be our guide to the meaning of the text. And that is also picking up on something that Professor Srinivas said yesterday about the untapped wealth of manuscripts in Indian scientific tradition. So it is a cautionary tale that it's not enough just to sit ourselves down with the texts that are already published and look at them in nice printed books or online. We have to get out there and read the manuscripts that have been have not been read for a long time, and we will find out much more, hopefully, about what actually was written. So along those lines, speaking of manuscripts, you may have seen a few years ago something of a media sensation about the famous Bakshali manuscript, a birch bark manuscript in preserving Sanskrit arithmetic techniques, and about modern technological analysis of the material of the manuscript. So it's a text that's written on birch bark, and very unusually for Indic manuscripts that have had to try to survive a very active subtropical climate, it is actually quite old. It is at least many hundreds, if not 1,000 or more than 1,000 years old in its physical form. And skipping over the headlines here, we'll just look at the summary about it. It was discovered nearly 150 years ago now, near what's now Peshawar. It has been kept for over 100 years in the Bodleian Library at Oxford. It consists of a compendium, combination of a manual and a textbook in a linguistically a form of hybrid Sanskrit that deal with a very wide variety of rules and problems in arithmetic based on what we can figure out about its script and its language and its mathematical content. It has been dated as a physical object to around the 8th to 12th century of the Common Era, but containing rules, containing mathematical knowledge from at least the 7th century and probably considerably earlier. And why it got a write-up in the Guardian newspaper is because at Oxford in 2017, various carbon-14 tests were conducted for dating small samples of the birch bark it's made of. And here's what they found. And they point out, rather breathlessly, but not unreasonably, that the identification, invention of zero is one of the greatest breakthroughs in the history of mathematics. And they say that radiocarbon dating reveals the fragmentary text, which inscribed on 70 pieces of birch bark and contains hundreds of zeros, as well as, of course, all the other digits in the decimal place value numbers, dates to as early as the 3rd or 4th century, the world's oldest recorded origin of the zero symbol that we use today, which is a reasonable summary of the results that were announced from the team that did the carbon dating. But the question is, how should we interpret those results themselves? They remark that the analysis indicated that the 3 samples attested from the manuscript date from 3 different centuries, one from the 3rd or 4th, another from late in the 7th to late in the 8th, and another about 100 years after that, 200 years after that. And note, by the way, that it is only the blank portions without any writing medium on the birch bark that were sampled. Now, again, as we did with looking at the Yavana Jataka evidence, if this interpretation is correct, this would, if this, that is when the manuscript was written at a period corresponding to this earliest date, that would indicate that the decimal place value numbers which appear throughout the manuscript were already fully developed by the 3rd or 4th century, which is exactly the sort of historical pinpointing we'd like to see. But is that, in fact, what the results, can we infer that from the results as we know them? And again, there is another more detailed article on this in the same journal I mentioned, History of Science in South Asia, if you'd like to look at the finer points of it. But we can summarize them here. Oh, good. The marks do show up pretty well. Because one of the things that makes the results they found rather anomalous is the fact that they sampled 2 consecutive leaves of the manuscript, which I show photographs of here. You'll notice that they look rather ragged and crumbly, and indeed they are. The birch bark of hundreds of years old is on which it was written is falling apart pretty drastically. But you can see, for example, this rather recognizable number 30 with a rather curly 3 and a 0 and a 10 here, and likewise a 10 and a 30 there on the next folio. So you note that here is the end of folio 16, V at the back of 16, and here is the front of folio 17. So 2 contiguous pages with a continuous stream of text on them, and they are dated by the carbon-14 analysis to over 200 years apart. So that gives us something to think about. And if we look more closely at the content of the text as it's written here, we can see that, in fact, it's referring to a single example problem in the topic known as Mishra, or mixed quantities. So, mixtures is a very classic subject in medieval arithmetic, discusses how you mix different substances of different concentrations together, what you get out of the combination. And this is an example involving alloys of gold. So these 4 gold pieces of weights 1, 2, 3, and 4 units have impurities of 1, 2, 3, and 4 mashas per unit of adulteration per unit respectively. So if they are all melted together, what's the impurity of the combined alloy? And this computation, I promised you no more mathematical procedures here, but you can probably easily see that this is where the 30 and the 10 come from. And you get a result for the total amount of the combined alloy. So, what does this textual nitpicking about this mathematical artifact tell us? It tells us that although these 2 consecutive folios have been carbon dated to 300 plus years apart, they're the continuous text that they contain, written very clearly as an uninterrupted sequence is referring to exactly, one unbroken problem, and also, as far as we can tell, in the same scribal hand. And as textual scholars, we kind of have to respect the inference that this, very probably indicates that they were written at the same time. So unfortunately, and with all due respect to the Guardian newspaper and the Oxford Radiocarbon Analysis Unit and so on, we have to say that the carbon-14 dating evidence is likewise inconclusive for the proposed 3rd to 4th century date. So, and this often happens, we keep on coming up with hypotheses that we think we can test to give us a more certain evidence about a particular stage or particular aspect of this historical development, and the hypotheses kind of fall apart on us. So what are we left with here? We're going to retreat to the information that we can, be sure about, and see what kind of narrative that gives us about the spread of decimal place value numbers within Indian culture areas. And we're still left with the knowledge that these were developed in India in the early Common Era. And I still think that the 3rd century, or from the 3rd to the 5th century, despite the stubborn lack of reliable evidence for it, is a perfectly plausible time frame for this to have happened. And we haven't even mentioned the possible contributing influences from other numeral systems that people in India at this time could have been familiar with. That is, the Chinese counting rod numerals that were not fully place value, as well as the Greek base 60 numerals that they took over from the Babylonians and denoted with letters of the Greek alphabet. And I won't go into details of those here. Those are both number systems that you can find out some, solid information about. Continuing our reconstructed narrative here, it seems most likely, just based on what texts these numbers show up in, that they were developed and refined by Indian astronomer mathematicians, Jyotishis, people working on questions of how to do computations specifically for calendric, astronomical, and astrological problems. And this seems, and again, we're stuck with speculation here, but it seems like a reasonable inference that on unique, why did this happen in India? Well, in the Indian knowledge system context, we have this unique scientific motivation of typically dealing with extremely large integers, anywhere from 10 to 13 or more decimal digits in cosmological modeling. In fact, ancient India is unique in the literate ancient world for having this long-standing, persistent interest in just expressing very large numbers. Other ancient scientific traditions can do that as if they need to, but they tend not to be much interest in it. In the Indian astronomical models, however, these are based on very large estimates for the lifetime of the universe on the order of 4 billion years, and the correspondingly large numbers of revolutions of the different planets during that time. And we were discussing before the start of the lecture about, what is it that you need decimal place value for that you can't do with other numbers? And certainly the place value principle itself, and I would argue the use of the decimal system with a nice manageable number of different digits to use, is pretty much indispensable when it comes to routinely manipulating very large numbers. If you are trying to set up the parameters of your astronomical system by coping with numbers that are in the billions or tens of billions or even hundreds of millions, then a non-positional system is just going to be incredibly complicated and confusing to deal with. We saw examples of the pre-Common Era non-positional decimal numbers where you have all different symbols for 1, for 10, for 100. Imagine if you needed 10 different symbols to represent having just one of whichever power of 10 it was. And to recap, we have our textual evidence indicating that the system was used by astronomers all over South Asia no later than the 6th century of the Common Era. And our epigraphic evidence from inscriptions indicates that it had reached much of Hindu and Buddhist Southeast Asia no later than the 7th century. So given that we're probably looking at a 300 to 400 year window during which this development happened, that was, it was not a immediate or universal adoption, but it really caught on remarkably fast, certainly among the scientific practitioners in whose interest it was to make use of it. So, pausing there for just to make sure we are all more or less on the same page before we leave the Indian culture areas. Do we have any questions about that? Okay. Then the first indication that we have of people outside the Sanskrit knowing world, what I'm rather clumsily calling Indian culture areas here, in order to do justice to the fact that Southeast Asia is very much a part of that process as well, is in quite soon after the period where the system gets established in South and Southeast Asia, namely around the 6th and 7th centuries. And the nexus of transmission seems to be the pre-Islamic Persian Empire, the Sasanians, particularly, if I can find, yes, Jundishapur here, a well-known ancient center of learning in pre-Islamic Persia, and as you can see, very strategically located for transmission to and interaction among people from all parts of South and West Asia. And this is the limited amount of information we have about this center of learning indicates that there were Indians as well as people from other places interacting there, studying and working on related subjects. And in the middle of the 7th century, which again is, only 150 years or so after we have our first definitive evidence in the work of Aryabhata of the existence of this decimal place value system in India, with a reference to the science of the Hindus, their valuable methods of calculation, their computing that surpasses description, done by means of 9 signs. Probably not indicating the absence of a 0, but simply that for later recipients of this system, it took them a while to figure out that 0 counted as a sign as well. I mean, the 9 signs were the 9 digits that referred to actual non-zero numbers. And the fact that Sebakht is in Syria is probably not at all coincidental, because you can see this is part of the area that is in that cultural ambit of the Sasanian international learning. We see a similar a reference to this several centuries later from the astronomer Abraham ibn Ezra of Spain in the 12th century, discussing what the learned men of India did to name all their numbers up to 9 and drew figures for the 9 numerals, and then a little circle like that as a sign for in a place where there was no numbers. So it is very clear from the beginning, the earliest reference to this knowledge, this arithmetic and numerical innovation, as it appears in West Asia, that it was associated with people in India, and it was appreciated as a very convenient and elegant system compared to the non-place value systems that they had been working with. And one really, I think, sealed the deal on this as a global phenomenon was the adoption of the decimal place value system, or Indian numbers, or Indian calculation in the very far-flung and very active Arabic tradition of mathematics and astronomy. The 9th century scientist Al-Khwarizmi, whose name survives in the word algorithm, wrote the most famous treatise on this, a Latin recension of which survives, but not in Arabic. And similar discussions of these Indian numerals, Indian calculation, give us information about why the numbers that we currently see, or the numbers we currently use, are different from the numbers that actually appear in Arabic scripts, which in turn are different from the number symbols in the Indic scripts that we saw several slides back. That is, there were Western versus Eastern Islamic numeral forms of these same numbers, but you can see the family resemblance there between these two systems, and also between those and the the Indic script versions that we saw before. So this continued in the work, eventually penetrating into European mathematics in the early 13th century work of Leonardo of Pisa, pointing out that he learned and in his instruction of among Arabic mathematicians and commercial calculators that was introduced to the 9 digits of the Indians, that is these 9 figures, and which, when combined with this sign 0, or zephyr or cipher from in Arabic from Sanskrit shunyam, any number whatsoever can be written. Again, this is where the appeal of the system to the professional practitioner really comes in that you have no limits on the type of number, the extent of number that you can express with a system like this. You don't have to wait until somebody has thought up a symbol for the next power of 10 you have to deal with, or the next power of some other base. You simply repeat the use of these same 10 digits, but just being careful about the place you put them in. You'll also notice something distinctive here, in that he writes these figures beginning with the 9 and going down to the 1. And this has been characteristic of the transmission process of the decimal digits throughout its absorption into Western mathematics, is because of the change of direction of writing from Sanskrit and other Indic scripts to Arabic and Persian, and then from Arabic back to the left to right Latin and Greek. People tended to get very confused about the direction that numbers should be written in. Eventually, in the Latin world, people settled on writing the least significant digit to the right, as was the practice elsewhere. but it took a bit of planning. Okay, so what I'd like to finish up with here is just a brief look at the process by which this knowledge of the acquired, wisdom of the Indian calculation became kind of diffused and mutated and ultimately lost entirely before being retrieved. And here is a sort of urban legend from our 12th century friend Abraham ibn Ezra, referring to a wise man of Aran, which is an Arabic version of the city of Ujjain, well known as a center of mathematical and astronomical learning, decided to come to the king in Baghdad for a large sum and taught the Arabs the basis of number, which lies in 9 characters. You can see there kind of, modified version of the historical facts of communication with scientists from India who came first to Jandishapur and then to Baghdad under the Muslim Abbasids and worked with the scientists there. But as with many urban legends, like the many in our day that attribute almost any, witty saying or discovery to Albert Einstein or Stephen Hawking or some other well-known individual, the historical specifics are attributed to this one person to whom they're almost certainly not actually due. More creatively still, we have a 14th century text in English, which is the creativity extends to the spelling here, who explains the word algorithm, which, as I noted, comes from the name of the Persian Muslim scientist Al-Khwarizmi, in which you use 10 signs of India that were found first in India by a king of that country, because, of course, whenever anything, important is developed, it must be the king, right? That was called Algor. That's not true. There was not an Indian king, Algor, who invented the decimal place value number system. That we know. But, again, this is how imagination and the desire to explain things get layered on the absence of facts. And similarly, continuing this development of a legend, the Indian origin gradually dropped out of these explanations, and the digits themselves were attributed to the Arab mathematicians from whom the European mathematicians had most recently received them, or with whom they associated with them. And again, you see some evidence of reference to the confusion about the direction of writing. They think that the numbers increase from right to left in their digits because that is the way that Arabic is written, which is in fact not the case. And here I think there are some interesting issues to look at in terms of modern historiography, how these forgotten learned men of India were rediscovered with, somewhat slowly and confusedly in increasing European direct engagement with India, and some things that we can infer about historical, the development of historiography of science in that process. And certainly I'm happy to share these slides with anyone who's interested in them and to discuss them. But I think we can leave our the lecture part of this, since I know we are approaching the end of our time, with a general summary here noting that, what we are tasked with here 2,000 years down the line from the events that we're interested in is the need to converge on, find consensus about historical explanations that are consistent with all the historical data that we've got, and that we need to be aware of the different cultural sources and contributions of the actual, historical actors in the process, and not just weight everything according to the culture that we think of as our source of science. And despite the somewhat disappointing results discussed in the Bakhshali manuscript, we also really have to engage with new technologies of artifact analysis, such as carbon dating, and again, just as much as we can, seeking information from the original sources that survive. So, thank you.